that volume's okay, and my mic volume's all right. Should be okay. So anyway, yeah. So if you, this is a paper by a guy named Pedersen, who's from Sweden, does a lot of scattering theory stuff, and then Sommer's a German, I think from Mainz. I'm not sure where Sommer's from. Could be from Jülich, Germany too. Anyway, so this is scattering from a polyethylene oxide in water, I think. Pretty sure it's in water. So in this, there's different temperatures here, 10 degrees C, 50, 100. And these are different concentrations. So this is, he's applying intensity divided by the concentration. He's also normalized it by the contrast squared, which doesn't change any. So that's just, basically it's intensity by the concentration. So, so in each of these, see, at each temperature, these are the concentrations, and each concentration, these are the temperatures. So the idea is that that this I naught, the intercept over here, is going to be related to the it's going to be proportional to, say, the basically the change in osmotic pressure with respect to the concentration. So that's because at those large scales, so when you're looking at this is large scale, so you're kind of looking at, so here you can see a coil as a spot, and then here you can see within the coil. And over here you just see like the density of coils. Right? So basically that thing is going to be, if you plotted the average density versus position, that's fluctuating. And it's those fluctuations that give rise to this delta rho square, but the density difference between the spots and the materials. You take one spot here, one spot there, they're separated by some distance x, and average that over the whole system. We can find out that this thing fluctuates without the average. Like this is the average value. It's just the density here. So anyway, that's what gives rise to this delta rho squared that he's like plotting here. So he's divided by delta rho squared, which is a contrast. It's like a contrast factor. And then the more stuff you put in, the bigger the intensity. So he's normalized by the concentration too. So basically, so this thing is also going to be proportional to the concentration. Like you can see here. So you can normalize that out. This thing, so this is an osmotic pressure. So we have like pressures, density, times RT for ideal gas law. And you can kind of expand that to 1 plus the second Bureau coefficient times density plus the third Bureau coefficient. And it goes on and on. Right? If you want to, so that's for gas, we have a bunch of atoms. If you say that your stuff here is actually acts like atoms, so that each of these, oh, sorry. So each of these dots, so this is this ideal gas, pressures, density, RT, and you have a concentration for the density. It's a number of concentrations, it's number per volume. It could be like density or concentration. So Anyway, so you can do a power series expansion to account for like binary interactions. Like this is ideal gas, means that things can pass through each other. And then if you have binary interaction, you have this term, you have ternary interaction, you have this term, you have other, you have other terms. So you do a power series expansion in that. Right? So you're kind of just considering the first term here. I mean, usually that's how it works. You just deal with the first term. So then if you want to know, in order to drive this, hey, so there's a penalty to increasing the concentration. And that increase is driven by KT. KT drives it up. And so there's going to be, that intensity is going to be also proportional to KT here. So anyway, so the thing that pushes it back down, that wants it to get to the average, is the osmotic pressure. There was a pressure goes up and then a higher concentration. It wants to reach the average pressure. This is the pi thing. Causes that. So if you want to look at how big can one of these fluctuations get, it's going to be like the change. How much does pi change with respect to concentration? So in other words, the pressure is going to push it back down. So it's like a change in pressure. Concentration is the thing that gives this osmotic force to depress that fluctuation. It's fluctuation being caused by KT. So KT's in the top, that increases the intensity. This change in osmotic is in the bottom, that decreases the intensity. So the bigger this d pi dc, the less fluctuations you have, and then intensity would drop. Right, and it's also going to drop with the, well, since this thing depends on concentration, right? So d pi dc is going to be like RT, and then you're going to have like B2 over 2 factorial, or over 2, right? And then B3, see, B2 times concentration times rho, and then B3 times concentration squared by 3, right? And all the other ones. So anyway, the polymer's B2 is like 1/2 minus chi times B naught. B naught being like the monomer volume thing. So this B2 can't have units of volume here. And then so anyway, so we have a way to measure chi here. So we can get this I naught, and we know what the temperature is, and we get this d pi dc. You take the derivative of this, you can get the chi out of this. So you can measure chi from how this thing changes with concentration. Right, so it's going to, d pi dc is going to be linear in concentration if you take the first term of the real expansion. So as concentration goes up, this guy goes up, this guy goes down. As concentration goes up, this guy goes up, the guy goes down, temperature goes up, this thing goes up, that goes up, but chi is actually 1b over t. So something like that. So this gets to be kind of complicated. Basically, as temperature goes up, this term goes down, and this term goes down, so this goes up. So temperature up, this term down, and then this term up. Okay. And then concentration up, this guy down. This thing's linear concentration. That's the rules to live by if I did it right. So this is I by C. So just remove the lead concentration term, and then concentration. Let's see, these are at fixed temperature, and then as concentration goes up, it goes down. And we already knew that. That's the blob idea, right? So concentration I up, down, that works. And the other one is temperature up. So these are same composition. And then circles are, see, it says here somewhere, 20, then 40, then whatever to 80. To the diamonds is 100 or something. 100 is triangles, I mean triangles. Right, so I goes up when temperature goes up. Right, so that's good, I guess. So from that, from the slope of that with temperature, you can get the chi parameter. And slope with well, first at the limit of this thing goes to 0. Or I didn't mention something with this thing too. So this is so with the gas thing, right, you're counting like how many, like the number of those things. That's kind of what this osmotic, the ideal gas is saying. This density is a number density, how many per volume, right? So anyway, with a polymer, the number is really like the mass divided by the molecular weight. It's 1 by n. You have to take, since chi is per monomer, so all your thermal stuff is per monomer, and everything else has to be kind of divided by the number molecular weight thing. So you have to, this is number per volume, but that number of monomers, number of polymer dots. Each dot is a polymer, not a monomer. So this row has to be by n. So this thing's by 1 by n for the first term here. This is how it works out. So this term basically becomes like 0 because n is 100,000. And this B term kind of dominates the thing. But if you go to 0 concentration, you can get the number average molecular weight from this. If you do a concentration series. So that's kind of how this works. So you can get the molecular weight of the change from this plot. But if you can extrapolate to 0 concentration, so if concentration goes to 0, then you get the molecular weight. So basically, this thing's going to, if you can do a concentration series and a temperature series from this thing, and then you use a simplified, like a Guinier approximation, plot 1 over I, because that's the compressibility factors. I is 1 over the compressibility factor. So you kind of want to get that compressibility factor out front. So this is a B2 times composition, and that's the 1 over n term. So when composition goes to 0, you get the molecular weight. So this axis is composition and angle both, because this is going to be Q squared is sine squared. So and you need, this is just a fudge factor to shift composition. So they just throw in a number. So Zim invented this. Bruno Zim was a guy at Brooklyn Polytech. Like when World War II came along, there were a lot of Jewish people that needed to get out of Germany. Bruno Zim was one of them. And a lot of them ended up in Brooklyn, New York. And that Brooklyn Polytech was already kind of like the best science school in the United States. It later went down. You know? Basically, there was no MIT. It was kind of like Harvard and the Ivy League. And there was like a technical school in New York City. So Brooklyn Polytech was it. So a lot of people flocked there. So like Zim was one of them. And then he did a lot of his work there. And then he moved to Santa Barbara later on. And it's like when he was dying. So anyway, so I mean way later on, like in the 90s or something. So I think he went to Santa Barbara at some point. But pretty sure he's dead now. But anyway, so these are plots. So you have different temperature up here. So these are isothermal lines. And then there's different concentrations going along that. And then these are constant concentration with different temperatures. Or, no, Q. These are isotherms. These are iso concentration. So if you're at 120 and then 150 at that concentration, you can see it gets to be a little complicated. This is just done on a computer now, but Zim needed a plot to do it. The idea is you're going to extrapolate. It's a double extrapolation. You're going to extrapolate in composition, extrapolate in temperature, get the molecular weight here. And then from the slope in Q at the lowest concentration from the slope, get the rate of gyration. That's just so this composition would go out, you'd have 1 over n times this times our Grenier's law, basically. So you can get the you can get the rate of gyration from the slope, and then you get the chi from the composition dependence. So like the slope of this thing gives you chi. 1 minus 2 chi gives you from the slope of this thing. So you can see there's a lot of measurements to do. I mean, you only have to make 5 samples. We have to measure the light scattering at all these different angles and at different temperatures. So these are like different angles at one temperature. Anyway, you get all of these points. You can make this plot and you can do this extrapolation. I don't think I've ever actually made one of these, except the computers will do it for you. So you just stick it in. There's a machine, like a light scattering machine. You put in you give it your 5 composition, it does a temperature scan, and it makes a plot for you. That's how I've done it. You know, basically, you can see it's a little bit. So this is like a workhorse in the early days, I guess. Nowadays you can put, nowadays what you do, see, there's a thing called a gel permeation chromatography. So the column is a gel, usually like a polystyrene gel, and you got to run some solvent through it, like THF. So it's got like THF running through it all the time, and then you inject your polystyrene sample at the same time. And over here, it'll have like an index refraction detector, which is just, it's like, so how the light gets refracted and passes through, which from that you can get, that's proportional to the density, how much material is in it, right? So yeah, it turns out that this gel is like a bunch of passageways, right? Some small, some big. So it's a fractal, some kind of continuous structure to it. It's not really that important. As long as you can kind of calibrate it. Right? So anyway, and to calibrate it, you just stick in like monodispersed polystyrene you can get, and you put in a bunch of different molecular weights, and you get like the time of elution time versus molecular weight plot. Something like linear. They can convert the time they went through the molecular weight. The way this works is that big things, so if you have a giant thing, it's going to follow, like, it can't go, so it's actually flowing so slow, the diffusion, the KT motion is governing the time. But it's going generally with a drift current going that way, right? But it's basically taking its merry time, like exploring on vacation, you know, oh, look at that island, you know, whatever. It's going all over the place. So however long it's gonna spend here, you know, depends on how big it is. The small things can go all over the place. So if you have like a motorcycle or you're walking, you can see every little thing. But if you're riding in a bus, it can only go down the main highway. You can't go on a dirt road. Right? So the buses get here first. Right? Then the guy on the motorcycle gets there later. So the smaller you are, the longer it takes to get out of this thing. This reverse what normal things are. Right. So, I mean, this wasn't the original thought. This was like, people figured out you could do a separation like this. Then they were like, oh, geez, like the big things are coming out faster. Why is that? And then they later on came with the bus theory. You know? So, I mean, these are like how things are kind of discovered. They didn't have a theory about gels, make a hypothesis and test it. They just stuck something in the gel and it came out that way. So anyway, so this thing, it turns out, will give you monodisperse. Like you can get monodispersed samples out of it. So C equals 0 because you're putting in like 10 milligrams per ml. Like there's almost nothing you're putting in. So once it comes out, like it's 0 milligrams per ml. But you can detect it with this. And also at this end, so you can have a laser, like a diode laser, and you can pick up some angle, like 90 degrees, and then you can have a light scattering detector on this. So and you can actually change the angle on that if you want, but usually it's like at a fixed angle at 0 concentration. And then you can get, you can kind of get So you don't need to do this concentration series because you're already at 0. So you already get the rate of gyration just by, well, if you do a couple measurements in angle. Actually, say I drew that on. There's going to be like diode laser, which is like a pen laser, right? So it's like $50. And then over here you have photodiodes, which are like $5 each, maybe. So you can have as many of those as you want. But basically, you only need 3 or 4 to do the angle extrapolation. You can't measure at 0 angle, but you can put diode lasers there. So then, as the thing flows on through, you collecting this light scattering at the same time. You already know, or you could use this calibration to get the molecular weight, but you don't need to, because if you have a light scattering detector, then it's going to give you this molecular weight, right? And because it's a single fraction, so the polydispersity on this is 1, right? Because you've taken a polydispersed sample that had a polydispersity, so you have like the, right, so you have, if you take like, you take the molecular weight and sum the molecular weight to samples, divide by n, and you get the first moment. Right, of the molecular weight. If you take the molecular weight squared and sum it, then you get the second moment. If you take the, so et cetera, right? So if you, this is called the number average. Right? And then this is called this is the second moment, but if you take, but the units of this are molecular weight squared. So you want to get rid of that. So divide by number average and you get the weight average molecular weight. And then this would be like the Z average. If you took N3 divided by N2, because the Z average is, you can go keep going if you want. Right? So the alternative would be you take the square root of the second moment, but that's not really done. Okay, so anyway, so the polydispersity index, so the way these work is you have some distribution, and number average is kind of in the middle. This is like number, and this is, number versus molecular weight. So MN's there, MW's here. There's a higher order moment, it moves out further. You get further into the distribution because you're essentially taking the moment of n times n, like molecular weight times the number versus molecular weight would be the second moment, and that's going to skew the curve, like make it have a peak further over. Like you're weighting this end more because you're multiplying by the molecular weight. So that means the peak of it's going to shift. Okay, so the higher order moments move over. So the polydispersity index is MW over MN. If that's 1, that means that it doesn't matter how I multiply it out. So how could that happen? That could only happen if I have like number versus like I only have 1 value. So if I multiply it by the molecular weight, it's still the same value. So no matter what, so it's monodispersed, I'm always get the same value, so it doesn't matter what the polydispersity. And if I take this thing and run it through my little column thing, I'm getting fractions that are monodispersed. I'm taking actual samples of this thing that are perfectly monodispersed. They ran through that column, they come out at different times. Right, so PDI for each sample in that column thing is going to be 1. That means that any moment that I measure number weight Z is going to be the same number. There's only 1 molecular weight for that fraction coming out. So that means I can actually reconstruct this curve from these real things where this is time, but I can convert time to molecular weight. Or for one of these things, so if I have a calibration curve, I can convert it. Like if I have that curve, I can convert it. I ran standards through it, convert it. But if I run light scattering on this thing, so if I run light scattering, then I can get this n here directly from it. Right? I'm at 0 concentration. There's no chi, so I can get the n directly, right? From extrapolating to Q0, I just get the molecular weight, and it doesn't matter what moment it is. It's just the number of that monodispersed sample that's coming out. Right, so if I stick an index thing on it, I can get the distribution curve. If I stick this thing on it, I can get the molecular weight of that fraction. And I can tell exactly what my stuff is. So if you, there's different ways to make polymers. If you make it by anionic polymerization, which is like a living, we call a living polymerization, so that all your polymers, like there's some anions in the group, put monomers in, they all start at the same time, so they're all going to be the same length. And then there's no termination to this because that thing's like a protected growth thing, so you can get basically a monodispersed sample out of that, as long as you have a protected end group. Then also with anionic, you can put in it, so you can grow it until all your styrene is eaten up, and you can put in butadiene, that monomer, this monomer, and you can grow that one. So basically, you can make like styrene, butadiene, styrene. You make these block polymer with fixed monodispersed molecular weights. If you do it with free radical polymerization, so that thing, if you do like number versus molecular weight, that you'll get one number basically. PDI is 1. If you stick in a free radical here, if you take ethylene, just put UV light on it, it makes a free radical. That free radical attacks another ethylene. Then you kind of have like a free, like a bush fire. Like all these ethylenes floating around are kind of combusting. You know, you have kind of just like a bush fire, like this one over here, it grows. So you get the polydispersity is going to be like 16. Right? Well, you might have multiple modes if it has like hydrogen abstraction, you get branches on it. It could be branched population. It could be higher than 16. So anyway, so if you have that sample and you want to know what this curve looks like, so the monodispersed one isn't that big of a deal. Like you're going to get a single value, the GPC is almost overkill. And any technique you use will give you the same molecular weight. But for this commercial sample of polyethylene, which is the most popular polymer, it's almost tied with polypropylene, I think. But anyway, so that, and polypropylene is going to be polydispersed like that too. So basically, you want to get that plot of this, put it in the GPC. The problem is for polyethylene, you have to run it at high temperatures. You have to have this whole thing heated to like 110 or 80 degrees C to solve it. That leads to kind of problems and can precipitate out in the polymer. So you need a special GPC for that. But for normal polymers, you just put in THF, the polymer, and zip it through and you get the molecular weight distribution. If you have a light scattering detector. You can also have a rheology detector, so a flow detector. And what else? Index of refraction, light scattering, and rheology are like the 3 ones. Rheology will get the intrinsic viscosity from it, which will give you the molecular weight. But if you combine those, you can tell this chromatography stuff, you can tell a lot about what the structure of the chain is, because the different techniques are going to look at different things. Like the viscosity detector is going to look at the hydrodynamic radius, the drag coefficient, which if it's branched, so the molecular weight, the light's going to give you the molecular weight. So if you know you have like a chain like this, that's 100,000, and you have a chain like that, that's 100,000. Right? This will have a smaller hydrodynamic radius than that one. Right? But the light scattering will give the same number, but the rays of gyration will be different too. Right? So if you have 3 or 4 detectors, you start to be able to tell the difference between these things somewhat. Yeah. So typically, like a polyolefin company where they run into this kind of thing, they're going to have like a whole floor of a building. If it's a decent company, they'll have at least a whole floor, if not a whole building filled with these columns, running all the stuff that's coming out, figuring out what every problem is that could possibly happen to this columns as they go through whatever they go through. So anyway, so is that business. Let's see. So the Zim plot is important, I guess. Basically, where you're going to run into it, you're not going to do one of these plots, most likely, but you're going to run into it in a GPC, which already has 0, it's already got the bottom curve because you're at monodispersed. It's going to do the angle measurement, and then you're going you're going to basically get the rate of gyration of molecular weight from that angle measurement. And then the chi measurement, you're not going to probably do in that. Right? So in fact, maybe the chi doesn't matter because you're just putting your polymer into some solvent. You don't care what solvent. You're just trying to get the structure of the polymer. So the chi isn't really of any importance to you, except it's got to be that it's soluble. That's the only thing that matters. Right? And you can tell that right away in the GPC. So you don't need chi, really. I mean, if you want to predict the future, will it be able to go into the solvent? Chi is useful, but if you just measure the molecular weight distribution, then you don't need chi. So you just get this zero concentration, right? So anyway, the Zim plot, I guess, never used much. I think you'd be hard pressed to find a paper. I might try to find a paper, but there definitely are papers. So all right, so there's that business. That's one part. That's one half of the world of getting concentrated, right? So the other half I talked about in regards to that paper. So you can see there's no structure in this thing. Like as you go up in concentration, these are isothermal, and they're going up in concentration. It's just flat, right? There's nothing going on. So whereas if you take polystyrene beads, monodispersed beads made by latex, or it could be sol gel silica in this, you can also make nano-sized beads from that. With surface charges, right, then you get this kind of curve, right? So it's going to be kind of similar to this in a sense. Okay, so you have the two scenarios here. That's weird. Oh, there, all right. So scenario one, or I. So this is called mean field. Mean average. And this is called specific interactions. So these are like two different worlds. They're like really separated from each other. Mean field is this, you have your chains. It's a whole thing about like the fleece, right? It's a fleece. And specific interactions are woven fabric. So in fleece, like you have a spinneret that's coming out, there's a conveyor belt. This is the way I understand it. I had someone offered just to go to the factory. All right, so making diapers, right? They make kind of a fleece in that. So they take polypropylene, shoot it out of the spinneret, and this thing is moving at like 50 miles an hour, the belt. And the stuff is just blasting out, right, to make a huge amount of this material. So apparently it's pretty impressive to see. I haven't seen it, but I don't think it's done in Cincinnati. Maybe it is. It might be. They might have a test facility for this. Anyway, so it makes this non-woven web. We call it a web, right? Mm-hmm. So it's basically the same as this thing that we're looking at. It's very similar, right? So except that it's a little bit like confined to a sheet, so there might be some orientation in it. But basically, it's the same thing as our polymer, and there's nothing going on there. In fact, they have something called spun bound, and the other opposite of spun bound, I don't know what it is, but spun bound means it's hot when it goes in, so it's a melt. So the fibers like penetrate each other. And then the other opposite of that, they don't. So they're like loose. So this is like theta condition. This is like good solvent. In fact, they have that fractal dimension. It says a dimension of 2. This has a dimension of 5/3. So really it's a pretty close analogy to polymer. Kind of strange, but anyway, that's all within this realm of mean field. Specific interactions, you have your woven fabric like this shirt, right? So, and these things are spaced. They have an actual real correlation distance, this squiggly thing, right? So they really have a real correlation distance that repeats in space. It's like crystal almost, right? So, and that would also be the case where you have these silica, colloidal silica spheres, right? So they have a charge, they have a repulsion, and they lead to this. They'll make a closest packed structure of the spheres. So anyway, so these are the two worlds. So one thing that's the same of the two is that the intensity at Q goes to 0 is still going to be 1 over this d pi dc. All right, so you still have this idea that and there's KT. So these things still have the idea like they're driven by KT to kind of disorder, which leads to fluctuations in density. Right, and then as they come together, it's osmotic pressure that keeps them from collapsing down. Right? So it's that pressure, like a gas pressure that has a volume. Right? So anyway, so that's going to be like second zero coefficient, makes them push apart. Same thing in both systems. So that I0 connects these two worlds. So you can. So if you look at just the scattering, you have log I by C log Q. And in this case, we have our normal, whatever, say it's Gaussian, and then as the concentration goes up, this thing drops down because this pi by C depends on concentration, because it's 1 minus B times concentration. Right? So, or 1 plus B times concentration. So that this thing gets larger, a bit smaller as concentration goes up. It's complicated, but that's how it works. So that's that. So this is the I0 over here. So over here, this thing, we have to have the same thing. Log I by C, log Q. So we have to have this thing dropping with concentration if the world's fair. If it's true, this thing depends on that, because both of them will have that same thing at large size. Now, it's my shirt. You can't tell the difference between a fleece and a shirt for a long distance. Right? So at some point, these things have to be the same, and that's at infinity, and that's at 0Q. Right, so, and then as you zoom in, then you see the structure, which is going to give rise to a peak. Right? So you have 2 pi over Q is that correlation distance. Right? As the concentration goes up, that thing gets smaller. It means it's got to move to the right, to the lower, to higher Q, smaller size, because Q is 2 pi over D or something, 2 pi over squiggly. Right? So basically that peak has to move over for these things as this goes down. So you're gonna have to get some kind of weird combination of these things to see what happens, right? So this is a sphere. The sphere has this is like a dilute sphere. Because it's a perfect structure, it's got this oscillation. Basically the spacing of those peaks, 2 pi over that spacing difference is a radius of the sphere. They're the perfect structure, right? So and then as you go up in concentration, this I naught drops. I think I have that here. Maybe I don't. Here. So this is S of Q is the structure factor. So in this kind of case, you take the dilute one. So you take, which is the sphere function. So
Yes, it's the.
oh, sorry. Right. This actually has to do with the homework. So we have spheres. So you look at dilute, so there's no interaction. And that's that curve I showed you, which is going to be this thing. This is roughly -4. That's kind of RG. That's Guinea's law. Right? It's called Perod's law. Right? The oscillations 2 pi over kind of the diameter of the sphere is the separation distance of those. So that's our dilute one. So we call that I0. Right? Then we're going to plot. So we want to get rid of that. Like that thing's just an annoying feature in the data that we don't care about, because the sphere is not going to change. If I make it more concentration, it doesn't change the sphere. So I take my I at some concentration C, divide by I0 to get rid of it. That's called the structure factor. That's a Q, because this thing is actually P of Q at the form factor. And this is the structure factor. So the intensity is P of Q times S of Q. And so if I take I divided by P of Q, then I get just the structure factor, which has to do with this, the thing that we're interested in. So So in other words, if I do that, I should get something cleaner. So what you get from an S of Q for this case for spheres is going to look like this, and you can see the peak. So the peak is the thing you want to see, and it moves to the right as the concentration goes up and it gets the smaller size. And then you can also see here as the concentration goes up, this thing drops just like it did with the mean field one. So down at this end, it's exactly the same show going on. Right? In fact, if you get to dilute, this is what our curve would have looked like without the correlations. In other words, this is like what our fleece looks like. It's going to be just totally flat and decay down. Because when you get to the high end of the fleece, it looks the same. And then when you get to the low end of the fleece, you see that 1 over d pi dc thing come in. So then it depletes when you get to the low end. Right. So this end here is exactly the same between mean field and specific interaction. The specific interactions come about like in here. And you see this peak goes to the right to get smaller. Because as you increase the concentration, the packing gets tighter. So that said, so qualitatively, you can get kind of a complicated description of what's going on here, but there's some hope of understanding it. Right? Quantitatively, this is absolutely a nightmare, because then you have to go to that, not the Ornstein-Zernicke equation of a 1 over 1 plus squiggly squared q squared, but the Ornstein-Zernicke of the h of r, c of r plus integral of h of r times c of r, where you need to have a limiting factor in order to solve the equation. It's recursive. I guess defined in terms of itself. It's h of r. It's like the structure factor of the thing is going to be the root 1. So the structure factor of the thing is going to be the root 1 plus the integral of the root 1 times the concentrated 1. So it means this is Joe. Joe is Joe. Right. And so if Joe changes and Joe changes, but you need to know like how Joe relates to Joe, and that's not going to be easy. And it's through like someone else, right? So you need to have some way, and this is just a loop that's going to go on forever. So you need a way to break out of that loop. Like, so you need some kind of approximation that says like, oh, I knew Joe when he was 10. You know, and if you can say what he looked like when he was 10, you can say what he looked like when he dies at 12 or 50 or whatever. And so, right, so you want to predict kind of the consequences of the thing itself. So it's a recursive. Whenever you have recursive, you have to kind of have an approximation to solve it. Right? And then that gets into like complicated that you don't need to know about. Really. I mean, you could if you want, but basically it's a bit too deep into the thing to really worry about it. And also, it doesn't really work. Like to fit these curves, it's not as easy. So the theory is probably okay, but the actual fitting of these curves, unless it's a really, really simple system, most systems aren't. Like say you take just dust and it charges up. Like say coronavirus, right? Is some particle, charged particle that's going to go into like a filter, like the N95s or charged polypropylene nonwovens. Same thing, made on a conveyor belt, but they do like a plasma to get a charge on it, so that it attracts the dust particles have charge on them, right? So you got some oddball, weird-looking thing. It's not a sphere, and it's going to have a peak in it like that, but so it's going to have a peak in it like that, but basically to fit that, to figure out what's really going on, there's no theory that's going to do that for you. Because polydisperse, it's pretty messy. Anyway, so people like physicists or physical chemists were really attracted to this area because it doesn't exactly have a good answer. And you can spend a lot of time kind of spinning wheels on it, I think. I mean, for our purposes, like we don't need to look except in the case like the level of that paper for the homework, you know. Which we get, yeah, just look at that for a second, because it's the same thing. Nice here. This paper she goes through. So here's the P of Q, S of Q. So that's the sphere thing. And the SDS micelles are kind of spheres, except that their shell, the core shell structure, so they have a middle, so the function is a little bit more complicated. It's like two sphere functions subtracted from each other. Then S of Q is just how they pack. It's the same thing. So I don't know. Let's see. She gives the sphere function, this thing somewhere. Well, maybe there's not much to say about this. That's the second paper. This is the first paper. This is the sphere function, except she messed it up, right? It's supposed to be sine. So the sphere function should be, I think this might be a question on the side. So it's sine of Q times the radius of the sphere minus Q times the radius of the sphere times cosine of Q sphere divided by Q times radius of the sphere cubed times 3. That thing squared gives you, that's the function. Then there's some contrast factor from this delta rho squared times the concentration, basically this intensity. Right, that gives this thing like whatever that. If you have like a core and shell, there's an inner radius and an outer radius. You can't take one of these functions minus the other function, and that kind of gives you a core and shell. It's a little bit more than that. That's roughly the idea. So it's sine, if you have sine, it's got this feature that this is plus, that's minus. If you take the average, that goes to 0. Right? Cosine has a feature that it's not, it doesn't have plus and minus like that. So cosine goes to some number. Then you have QR divided by QR. So at high Q, you're averaging out a lot of these. If you're doing a lot of oscillations, so it just averages out. Then you have QR over QR cubed. That's 1 over QR squared, and it's squared because you're like 9 over Q to the 4. R to the 4, so this is kind of the surface to volume ratio for the Pro's law minus 4. So log on is like Q. So this function works for Pro's law. You can get the Guinea's law out of this because sine is 1 plus x cubed over 3. So it's x plus x cubed over 3 factorial x5 over 5 factorial. And cosine is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, it means a series, right? And so if you're looking at, I looked at high Q, I got this. I look at low Q, I go to the series because the powers cancel out. And this is minus QR, so it's QR, so it's x times cosine of x, right? So times x, I have x, then cube, then 4. And then I subtract those two, so these two cancel. And x cubed over 6, or x cubed times 1/6 minus 1/2. And then x, this becomes, because it's times x is 5, so x5. And I'm dividing by x cubed, right? So that this becomes actually x to the 1, and this is x to the 2. That's negative, and then it's 5 factorial. So 3 is 6, 4 is 24, 5 is 100. 20 or something. Minus 3.6. Find the common factor. Guess that's like 20 minus 1. So anyway, you can figure this out. You'll figure out that this ends up being 5/3 or 3/5 r squared, which is rg for a sphere. I mean, it'll work out exactly right. And then that will give you Guinea's law. That's the argument of 3/5 r squared. So this thing will give you Guinea's law and the power law if you do these series things. I think that might be a question in the homework. So you just have to kind of figure out the common denominator for those terms, and we'll work out for it. So anyway, this thing obeys like Guinea's law and also obeys Perot's law. So that means it's a valid function. It looks okay. It behaves the way you expect. It's a solid sphere. It should have a surface. I think even if the surface to volume for a sphere is going to be like 6 over r or something, because it's 4/3 pi r cubed 4 pi r squared. So you end up with, and this is for r, so this will be 3 over r. So you end up with that this thing ends up being 3 over r for whatever, for the surface to volume ratio would be the prefactor for as well. You can get that too. Everything's in this that function. So that's a popular function. Like that's why you remember it's like kind of like one of the more popular, because everyone wants to say things are a sphere. So and you can build the concentric, the hollow sphere from that function. You can also build the ellipsoid from that function. So with ellipsoids, hollow spheres, hollow ellipsoids, and spheres, that kind of approximates most things. If you get more complicated than that, you can't solve it. It's going to be too complicated. So that kind of solves most things. Anyway, so I think that's probably like some of the homework. I think there was a question on that. Anyway, see, she didn't put the QR here in front of the cosine. It's missing. That's kind of messy. It's not a clean thing. So someone should have noticed that at some point. So that's that business. I don't know what the questions were. Well, 1 minute, so I could kind of look at that. So the questions are. I guess it doesn't ask about the sphere thing.
Yeah, it's about the other.
Yeah, the other function. Yeah, so you can do the sphere thing too. Yes, another one. So anyway, I guess we're kind of out of time. So next time I just want to go through the this hydrodynamic radius business. Kind of go through basically the intrinsic viscosity measurement. How you get that's like the simplest way to get it. That would be a detector on the GPC. So the GPC you would use. There's actually two machines we use: GPC and dynamic light scattering. I like the easiest thing. So GPC, it'll have a viscosity detector and get this intrinsic viscosity, and that gives you the hydrodynamic radius. So we'll go through kind of how you do that. It's not hard. This is a viscometer. We can also measure it. So, all right. So I'll see you guys on Wednesday.